In this video, I'm going to be presenting the discrete time IIR filter group project number 1 for EC101 Winter 2024. So a quick rundown on what I'm going to be covering today. We're going to go over the digital filters and specifically about FIR and IIR filter, the examples of each of them, and the proof of why they are either FIR or IIR filter. And at the end, I'm going to be talking about the experiment that we conducted as a group in using a DT EMA filter to filter out the noise of the data that we retrieved from the MPU 6050. So, without further ado, let's dive right in. So let's start with the theory. So what is a digital filter? Is essentially a software, a mathematical algorithm implemented in hardware or software that operates on a digital input signal. So it takes in a digital input signal to produce a digital output signal. And this, because we are working with digital filters, that means they have a fixed sampling rate. So fixed sampling time is the T, and then that's related with the sampling frequency by the equation. And we want to choose the sampling frequency in such a way that is at least twice the bandwidth of the input signal to avoid aliasing. So here's the rough diagram of what's happening. So we have a continuous time signal. We want to apply analog to digital converter to get the discretized version of the signal x of n, and we run through that to the digital processor. This is where the digital filter ring comes in to get the y of n, and then to get to the y of t, we run digital to analog converter. And what's the advantage over analog filter? They are programmable. Like I said, they are just software. You can code it, and they are robust to noise and faults because unlike analog filters, you are not prone to measurement errors, no temperature variations, and manufacturing variations. That's a big one, and they're also easy to design. So there are two main classes of digital filters. So the first one is FIR, final impulse response, and IIR, infinite impulse response. We'll see why they are named in such a way. And in general, a digital filter can be represented by its impulse response h of n, because if we know the impulse response, we know everything about the digital filter, what's going to happen given an input signal. And so impulse response refers to the appearance of the filter in the time domain. So you have the frequency domain and the time domain. So if the filters usually have a broad frequency responses, that means that corresponds to a short duration pauses in the time domain. So before we dive right in, let's recall the general form of the LTI system, the linear time invariant systems. It is for non-causal system. So for DT signal, we have the sum from minus n1 to n2, where they are both positive integers, of a of k, which is coefficient of y over y of n minus k, and the same thing similar happening for the x of n minus I. And for the continuous time signal is similar, except instead of difference, like y of n minus k, right here you have derivatives. So it's over order of minus k to k. And also if it's minus, that means this is just integrals, because the reverse of derivative is just integrals. So to get a causal system, that means we want to set m1 and n1 to be 0, because we don't want it to depend on, you don't want the current output to depend on the future output or the future input. So you want only to depend on the previous outputs or inputs. Hence, we set that to be 0. And so let's look at the special case. So when n1 and n2 both are equal to 0, let's look at it again. That means the top two with the top. So that means we're just only getting a 0, and we bring it here. And here's just to for simplicity. And here we can see that the output only depends on the inputs, and hence this is a non-recursive equation, because we're just using the inputs to get the output. And this tells us that this is a FIR system. So what are the properties of an FIR system? Is that why the output will always go back to 0. eventually, because there's going to be some time over that past M2 where the input is no longer there. That means y of n is going to go to 0. That means it's going to be always stable because it's going to die down eventually. And the second one is that the coefficients of an LTI FIR filter are the values of the impulse response themselves. We can see it right here because we apply h of n. This is the again using the difference equation of right here, and to get the impulse response, I should mention this earlier, is that we set the input to be the delta function, the impulse, and this is a representation property, so you just only get this. And the output is the convolution of the input signal and impulse response. And why is that? Because again, from the difference equation up here, and since we know that from the previous line that this coefficient is basically the impulse response, so we set that at y of k, and then y of h of k times x of n minus k. That this is basically definition of the convolution, and so we just write x of n convoluted with h of n, which is very neat. So let's take a look at the example of a FIR filter. This is called the moving average filter. This is quite well known. So what's the difference equation of a MA filter? So we have this, the term at the front. This is basically the coefficient at the front. This is the AKs, but we're setting all the coefficients to be all the same, to be the length of the filter, which is L right here, M1 times plus M2 plus 1. The plus 1s comes from the fact that we're going to go through k is equal to 0, and hence the plus 1. And then we just times x of n minus k right there. And to get the impulse response, we just set the input to be the delta function, and this is basically just the 1 over the length of the filter, and this is only when n is between minus m1 and m2 and it's 0 everywhere else. And to get the frequency response, we do it as h of e to the j omega. This is the equation, the formula for that. It's the impulse response times the e to the minus j omega k. And h of k, we can pull it out since it's just a constant 1 over L. And to sum up all of these, using the sum of the finite geometric series, we get this. This is the general form. And so why is the moving average filters an FIR? Well, what makes an FIR filter? So the FIR filter means the impulse response is of finite length, hence the name finite impulse response. And that's the case because we have the length is this between this, and it's 0 everywhere else. That means the length of the h of n is only the length of the filter, which is definitely less than infinity, assuming that m1 and m2 are finite, of course, but that's always the case. And another way we can say that is that sometime past m2, the convolution is going to be 0. So that's what I said earlier, that it's going to dial down eventually to 0. And that's a characteristic of an FIR filter. And this is another proof of why the moving average filter is an FIR, is when the poles of an FIR filter are only found at z equal to 0 and or z equals to infinity. And so we find the transfer function, and then we get this, and then we determine the poles, and then we indeed only find the poles at infinity and at 0. So thus this is an FIR filter. I don't want to go too in depth on this because we have a lot to go through at the end. So that's the first special case. So now let's consider when n1 and n2 are both not equal to 0. That means we're gonna have, in addition to the inputs, we also gonna depend on the previous or future outputs of the system. So the output of the system depends on the previous or future outputs, and that essentially is the IR filter. And one of the properties of that is that it is recursive, because once we have the output, we're gonna put it back to as the input, and then we get the output, and then we put it back again. So there's like a feedback loop built into the system. And how about the stability? Sometimes it depends on the system, the difference equation itself. Sometimes it's stable, it's nice. Sometimes it behaves quite crazy, so we can't really tell. And it is fast, low order. That means for the same kind of like filtering effect, the fewer orders needed for the IR filter compared to the FIR filter, so that the amount of computation is faster. Hence, sometimes that's why IR filter is preferred over FIR filter. And then sometimes it will asymptotically nearing to 0, but it will never becomes 0, like realistically, and we will see that in a couple examples. So the first example is the EMA Lowpass Filter. EMA stands for exponential moving average. So moving average is exponential. It provides a contribution of new information through the measurement x of n and a smoothing effect based on the memory provided by previous filter value. So this is the difference equation: alpha times x of n, where alpha is some value between 0 and 1, plus 1 minus alpha, so that's the complement, and we take the complement, and then times the previous output. And alpha controls how aggressive the filter is. So the extreme cases when alpha is equal to 0, no effect on the input at all for the input, and while alpha is equal to 1, that means the filter is not like actually filtering at all. And why is it called exponential? The weighting factor of the previous inputs decreases exponentially, and we will see that on the graph later. So why is the EMA filter is an IIR? Well, this is typo. Why is it for FIR filter? The filter for IIR is if the impulse response is infinite in length, hence the name infinite. So we want to find a closed form for the reconciliation from the difference equation. So we basically taking the y n minus 1, and we plug in the same thing but when n minus 1. So hopefully we can see that, and then we keep on doing the same thing until n, and we're basically we get this sum. So this is the closed form. And so to find the impulse response, again we set the input to be the delta function, the impulse, and we're left with this alpha times 1 minus alpha to the n. And so if we take the limit, since alpha is between 0 and 1, that means the limit's gonna be going to 0. So it is 0, but that means h of n will have infinite length. That means it's IR. As I said, it's asymptotically nearing to 0, but will never go to 0 because it will have to have infinite in length. So this is the example when alpha is equal to 0.22. The impulse response is graphed below. As you can see, it's like a nice exponential curve, and hence the name's exponential moving average. So to find the frequency response of the EMA Lowpass filter, we first find the transfer function. We take the z transform first, and then we apply y of z over x of z, and that's the transfer function, and we get this. And notice that we have the pole at z equals to 1 minus alpha, like right here, this term at the bottom. And recall that if you have poles other than 0 and infinity, that means that's not an FIR filter. That means it's a IR filter. So the frequency response is this. This is the same formula as the last time, and then alpha times, this is just alpha times whatever inside of this, and this is a sum of infinite geometric series, and this is the final value, final formula. Yeah, so that's the EMA Lowpass filter. So let's take a look at the other example, echo removal system, and this is the difference equation, y of n plus alpha y n minus capital N of equal to x of n, where again alpha is between 0 and 1. And then we want to unravel, do the same thing to get the closed form, and we get this when y is equal to y at k times capital N is equal to minus alpha all over to the k. And if we set n little n to be k of n, k times n, we get this, and n must be a multiple of capital N. And to find the frequency response, we do the same thing, find the z transform and then find the transfer function, and then we just plug in e to the j omega as in place of z, and we get this. And why is it IIR? Again, that we see that the limit is 0, and that means h of n has to have infinite length. And another proof is that for odd capital N, we have pole at minus square root of n root of alpha. Yeah, so that means it's not, they have root other than 0 and at infinity. So here are some references that I use for making the theory. And so we're gonna get to the experiment really quick using the MPU 6050. And so this is the part of the code. I don't want to show the code, but here's essentially like how we gather data from the MPU 6050. This is pretty standard. We just get the accelerometer values for in x, y, and z direction, and also the gyroscope angle from in the x and y and z direction. And this is like the implementation of the DT EMA Lowpass Filter. So remember, that's the IIR filter that we use, and then we take the current, the previous input, and the float, the alpha, and this is the difference equation essentially. So here are the results. We just taking the accelerometer in this case in the x direction, and then we have the noisy and filtered, and then y direction noisy and filtered. And as we can see that then the filtered are much smoother compared to the noisy, and we can see that here in all three. And then let's take a look at the video demonstration really quick. So yeah, as you can see that the filter signal is much smoother compared to the noisy signal as we move the MPU 6050 along. Yeah, and the same thing goes in the other directions. So yeah, so that concludes the presentation for this video. I hope you learned a lot, or learned something at least, and I hope you find this interesting. So thank you for watching. Bye bye.